In our discussion so far, we focused mainly on reasonably static models of what's happening with the aircraft. Let's now move on to the more dynamic environment and manoeuvring flight. In this section, we'll look at stability, side slip, dihedral effects, and the mechanics of manoeuvre. So first of all, let's talk about stability and revise what we mean by stability. When we say that something is statically stable, we mean that if it's disturbed from its current position, then it will tend to return to the original position it held before the disturbance. Looking at these three simple diagrams then, the first shows a positive static stability. If the ball is disturbed from the bottom of the cup, it will instantly try to go back to its original position. In the middle diagram, if the ball is disturbed from the top of the cup, it will become increasingly divergent, and so we say it has negative static stability. The third diagram shows a flat surface with a ball that's simply translated from point A to point B, and in this case there will be no tendency to either diverge or to return to the original position. Then in this case we say that the ball has neutral static stability. All transport aeroplanes will have a degree of positive static stability. The benefits of this are that a slightly disturbed aircraft will tend towards its original position, which allows for some unattended operation. We don't have to constantly fight the aeroplane to keep it on the parameters we want it to be. And this allows for some tactile operation versus the trimmed speed. For instance, if we start flying slower than the trimmed speed, we'll find that we need to maintain a back pressure on the controls in order to keep the aircraft from descending. There are two other types of stability which we can consider. The first is manoeuvring stability, which is the aircraft to tend back towards its original trimmed load factor, which naturally normally will be 1g. And the second is Mach stability, that is the tendency of an aircraft to hold a given Mach number, because if it speeds up, the drag will increase, and so the aircraft will tend to slow back down to its original Mach number. Looking now at side slip. Transport aircraft are normally flown at near zero side slip, and aircraft are designed to be directionally stable due to the vertical stabilizer. Therefore, if we do find an aircraft in side slip, it will be pilot commanded, assuming, of course, that we still have symmetrical thrust. If we find ourselves no longer in directionally symmetrical flight, the dynamics can be really quite complex, and this can generate large forces and moments in all three axes of the aeroplane, and particularly in roll and yaw. So, what do we mean by a side slip? Well, this is the situation where the relative airflow no longer approaches the aircraft from a head-on perspective. Instead, it's canted off to one side, and what we'll find is that the rudder is deflected to one side. In this case, we have the rudder deflected to the left and the control column right to counter the tendency of the aircraft to roll to the left. And now we have the aircraft's velocity no longer following the longitudinal axis of the aircraft. So what we can say is that an inappropriate use of the rudder will generate a side slip, which could cause a rapid rolling moment which has a time delay element to its onset. The rapid roll will be affected by several factors which we'll explore in a second, and the time delay coupled with the rate of the roll may startle pilots and induce an over-controlling situation. This over-controlling may induce rudder forces which exceed this airframe structural limitation. So we as pilots should learn to feel the lateral forces through the seat of our pants and also monitor that the slip ball is centralised. Developing this intuitive feel for the aircraft, where you can feel that you're being pressed to the left or to the right, is an important point for us in considering effective upset recoveries. We talked about the roll rate in a side slip being potentially very large. So what is it that governs this? Well, first of all, there's the angle of the side slip, the angle now between the relative airflow and our longitudinal axis, the green line. The second point is the crossover speed, that is to say, at a set rudder deflection, which may be maximum in your aircraft, there will be a speed at which maximum aileron or spoiler in the opposite direction cannot counter the roll as a secondary effect of the yaw. This is dependent on our weight, our configuration, and importantly our angle of attack. So for us in upset recoveries, when pitching up, increasing the angle of attack, if we are yawing with a high roll rate at the time, we will aggravate the upset, not resolve it. Therefore, if we are going to effectively recover from an upset, the rudder should be neutral before we increase any angle of attack. The third factor influencing the roll rate of the aircraft due to side slip will be wing dihedral effects, and we'll take a closer look at those now. So dihedral, of course, is the term which we use to describe the angle at which the wings are mounted on the fuselage. This dihedral gives us a stable rolling moment with side slip. The wing to the side of the relative wind will develop more lift and will therefore counter the yaw-induced roll. Sweepback angle is also significant, and whilst its primary purpose is to delay the compressibility effects at high Mach numbers, it does also have a dihedral effect, a corrective effect in side slip. That is due to the fact that the wing furthest away from the relative wind has less frontal surface area and so is producing less lift. With an increase in lift comes an increase in the induced drag, and therefore the increased drag on the wing on the side of the side slip will create a yaw into the relative wind. Moving on now to the mechanics of manoeuvring flight, and let's consider some basic examples to explain the forces which we feel when flying in different conditions. First of all, the example where the aircraft is climbing. Weight will always act towards the centre of the earth, and we must generate an amount of lift to counter that weight in order to remain in a steady state. The lift produced by the wing will be greater than the magnitude of the weight. Drag will always act to slow the aircraft down, but in addition to the drag, we also now have a component of our weight vector which is acting in the same direction as drag. So the drag plus the drag component of the weight will give us the amount of thrust that we require to hold that climbing angle without accelerating. And so to achieve a steady climb at a constant airspeed, we need the thrust to equal the drag plus the drag component of the weight. And also, lift must be greater than the weight due to the angles of the vectors. In a descending scenario, we still have weight acting towards the centre of the earth, lift to counter, drag, which will be acting to slow the aircraft down. But this time we have a component of the weight vector acting to counter the drag. So this time the thrust that we will require will be the drag minus the thrust component of the weight. So to achieve a steady descent, we must have thrust less than drag due to the component of the weight which acts to assist the thrust. Let's now look at turning flight. In the example where we are wings level, if the aeroplane is in a steady state, then the lift will equal the weight. When we roll to an angle of bank, the weight will still act towards the centre of the earth, and we will still need a vertical component of our lift to counter the weight. To achieve this, we will now need to increase the amount of lift that the wings are producing, and this will also give us a component of the lift which is pointing towards, if you like, the centre of our turning circle. And it's this horizontal component of the lift which produces the turn, because it is now giving us a resultant force which is not countered. Thinking back to Newton's first law that we looked at much earlier in this trajectory, an external force is now acting on the aircraft and is not balanced by any other force, and so we get an acceleration, in this case the acceleration being the turn. So what we can say is that lift in the second diagram is greater. We know that the wings can only produce up to a maximum quantity of lift before they reach their critical angle of attack and stall. Therefore, when we're trying to recover from an upset, it's not efficient to try to pitch the nose back to the horizon unless the wings are level. And additionally, above approximately 66 degrees angle of bank, trying to use pitch to recover the nose of the aircraft back to the horizon will very likely exceed the aircraft load factor limitations. So what can we take from this slide in summary? If we have the nose above the horizon in a climbing attitude, then to reduce the rate of speed loss, we will need to increase thrust. If we have the nose below the horizon, in order to limit the rate of acceleration, we will need to reduce thrust. And if we find that the wings of the aircraft are not level and we need to achieve a pitch up to recover the nose back to the horizon, it is not efficient to start that pitch until the wings are rolled to be parallel with the horizon. That is to say, wings level. So let's look now at how we achieve that wings level flight through our lateral control. At the risk of stating the obvious, control and roll is achieved by ailerons and spoilers. And in most modern transport aircraft, adverse yaw caused by the differential in drag between the two aileron deflections is often counted automatically. Now, remember from our control brief that we said that ailerons lose effectiveness on the downgoing wing at high angles of attack, and spoilers can lose their effectiveness beyond the stall. So, whilst it's true to say that transport aircraft need to demonstrate positive, unreversed lateral control up to the point of stall, beyond the stall no generalizations can be made. And so, it's critical to reduce the angle of attack at the first indication of a stall in order to preserve control. Additionally, as we saw in the last slide, it's important that we consider the direction of our lift vector in upset recovery, and we need to orientate it to be pointing above the horizon and preferably wings level before we start that pitch up in order to maximise the rate at which we can achieve the nose pitching back to the horizon, and also to make sure that we remain within the load factor limits for our aircraft. In the diagram here, you can see that with the aircraft with the red lift vector, we have an exaggerated example of why pulling to try to achieve the nose to pitch back to the horizon will simply not be effective. In the second diagram with the aircraft with an amber lift vector, we can see that we probably will achieve the nose back to the horizon by pitching up, but we're not at our most efficient. The ideal example, therefore, is the aircraft with the green lift vector, where we can use all of our maximum lift capability to achieve the nose pitching back to the horizon with a minimum height loss. Directional manoeuvring, then, is achieved by rudder. The rudder in most modern transport aircraft is exceptionally effective, and when the aircraft is symmetrical, i.e. we have no engine failures, a high rudder deflection will induce side slip with the risks that we've already seen and discussed. To prevent structural damage due to the effectiveness of the rudder, most aircraft have protections, but be aware of your own aircraft type and understand how they work. The load factors experienced by the airframe with a maximum rudder deflection at anything but slow speed could be enough to cause the tail of the aircraft to detach from the aircraft. Some aircraft may change the gearing of the forces that you feel according to the speed that you're currently flying. And some aircraft may have a limit to the extent of rudder travel according to the speed that you're currently flying, but these may maintain the same gearing ratio, giving you the same control force for the same amount of rudder deflection. In any case, be very cautious of the application of rudder during upset recovery. Modern transport aircraft will exhibit positive static directional stability, but this comes with its own risk of Dutch roll, and so we have yaw dampers to assist with negating this negative effect. Dutch roll, for the avoidance of doubt, is where the nose of the aircraft will end up tracking through a profile that looks something like an infinity sign or a number 8 lying on its side. Dutch roll can be problematic in as much as there is a potential for it to become divergent. And so if you experience Dutch roll, have a look to see whether your automatic yaw dampers failed. And the rule of thumb is that if you suspect you're in a Dutch roll situation, slow down and go down, decelerate and descend. To summarise this section, we've looked at the stability of an aircraft and revised some concepts. We've discussed side slip and the dangers associated. We've examined dihedral effects on the aircraft and how that helps to correct side slip. And we've discussed the mechanics of manoeuvring flight.